Hello everyone, welcome to this class. In this video, we're going to focus on differential and integrated rate laws. Rate laws describe the progress of the reaction. They describe the relationship between reaction rate and concentration of reactants. If we take reaction AA plus BB gives us products, we can write the rate expression like rate is equal to rate constant K multiplied by concentration of A power small m multiplied by concentration of B power small n. Here small n is the order of reaction with respect to A and small n is the order of reaction with respect to B. And the overall order of the reaction will be m plus n. It is not possible to predict the rate law from the overall balanced chemical reactions. Rate laws must be determined experimentally. Differential rate laws expresses the rate of reaction as a function of a change in the concentration of reactants over a particular period of time. They are used to describe what is happening in the molecular level during a reaction. These rate laws determine the overall mechanism of reaction by which the reactants turn into products. If we take a hypothetical reaction, A gives us products, so we can write rate is equal to negative sign change in concentration of A divided by change in time is equal to rate constant K multiplied by concentration of A power small n. Here small n is the overall order of the reaction. The above expression tells us about the rate of reaction at a particular instant. If we know the rate constant and the concentration of reactant, then we can find the rate of the reaction. Now, we will talk about integrated rate laws. Integrated rate laws express the reaction rate as a function of the initial concentration and a measured concentration of reactants after a specific amount of time has passed. They are generally used to determine the rate constant and the order of the reaction from experimental data. Now we will talk about zero order reaction. For zero order reaction, we can write the rate expression like rate is equal to rate constant K multiplied by concentration of reactant power 0, because the reaction is zero order. Some example of zero order reaction are the reverse Haber process. The decomposition of ammonia at platinum surface gives us nitrogen and hydrogen. Reaction between hydrogen and chlorine in the presence of light gives us HCl. It is a photochemical reaction. The decomposition of hydrogen iodide at gold surface gives us hydrogen and iodine. The decomposition of nitrous oxide at platinum surface will give us nitrogen and oxygen. Now we will derive some equation for zero order reactions. Let's take a reaction. A gives us products. At the start of friction, that means T is equal to 0. Let's say the initial concentration of reactant is small a, and at the start of the reaction, there is no product, so the concentration of the product will be 0. After some time, T is equal to T. Let's say the drop in concentration of reactants is X and the increase in the concentration of products is X. So the remaining concentration of the reactants will be A minus X. Now we can write rate is equal to negative sign change in concentration of A divided by change in time is equal to rate constant A multiplied by concentration of A power 0, as it is a zero order reaction. So negative sign d dt. So the remaining concentration reactant is A minus X is equal to rate constant K. So if we differentiate with respect to time, we find dx upon dt is equal to K. We can write dx equal to K multiplied by dt. Now we have to integrate. So we will integrate from 0 to x, that K is constant. So we will integrate from 0 to t. So after integrating, we found x is equal to kt. Here x is our drop in concentration. So if at the start of reaction initial concentration is A and the drop in concentration is Kt, so after time t the remaining concentration will be A minus Kt. Now we will derive the same expression in another way. Alternate derivation. As we know, we can write rate is equal to K multiplied by concentration of reactants power Z. So we can write negative sign dC upon dt. Here dC is our change in concentration of reactants divided by change in time. So we can write dC is equal to negative sine K dt. Now we will integrate from initial concentration to final concentration. And time will be 0 to t. So we can write Ct minus C naught is equal to minus 8. So we can write Ct is equal to C naught minus Kt. Now we will rearrange the expression. Ct is equal to minus Kt plus C naught. Now we compare these expression with a equation of straight line. As we know, the general equation of a straight line is y is equal to mx plus c. Here m is the slope of the straight line and c is the y-intercept. So this Ct is our y, this C naught is our C, that means our y-intercept, and T is our x, and the slope of the straight line will be minus k. So if we plot a graph where we take time in the x-axis and take concentration in y-axis, so our concentration of reactant will drop linearly. And the slope of the straight line will be negative sign k. And this y-intercept is our C naught. Now we will learn a very important property of zero order reaction. Let's take the initial concentration of reactant is 100. After 5 minutes, the concentration is 80. Then after 5 minutes, the concentration is 40. After 5 minutes, the concentration is 20. And then after 5 minutes, the concentration is 0. Here we can see in every 5 minutes, the concentration drops by 20. So we can say that equal amount of drop in concentration happens in equal amount of time. This is the property of zero order reaction. So this property is very, very important, and by using this property we can solve many mathematical problems regarding zero order reaction without writing any single equation. So the property of zero order reactions means equal amount of drop concentration in equal amount of time. Now we will see some other graphs, like if we take the drop in concentration x in y-axis and take time in x-axis, we can find a straight line that passes through the origin, because we know x is equal to kt, so we can compare with y is equal to mx. So we know that y is equal to mx is the equation of a straight line that pass through the origin. We take rate in y-axis and time in x-axis. We will find a straight line that is parallel to x-axis, because the rate is equal to k multiplied by concentration power 0. So as time progresses, the rate of the reaction will not be changed for a zero order reaction. Now we will find completion time and half life for a zero order reaction. We know Ct is equal to C naught minus rate constant K multiplied by 10. At completion of the reaction, the final concentration or remaining concentration will be 0. So we can write C naught minus Kt is equal to 0. So we can write T is equal to C naught upon K. So this is our completion time for a zero order reaction. Now we will calculate half-life for a zero order reaction. So we again write the expression Ct is equal to C naught minus Kt. At half-life, the remaining concentration is half of initial concentration. So we write C naught upon 2 is equal to C naught minus Kt. So we can write Kt is equal to C naught minus C naught by 2. So Kt is equal to C naught by 2. So our time will be C naught upon 2K. So our completion time will be C naught upon K, and our half-life will be C naught upon 2K. Now, if we take a reaction like Na Dixous products, so for this kind of reaction, our remaining concentration Ct will be initial concentration minus mKt Our drop-in concentration will be nkt. Our half-life will be C naught divided by 2nk, and our completion time will be Tc C naught upon nk. So we just need to remember this formula, then we can easily solve any kind of problems related to zero order reactions. So this is our video regarding zero order reactions. In the next classes, we will derive some expressions for first order and second order reactions. So I hope everyone understands the concepts very well, and thanks for watching this video, and don't forget to like, comment and subscribe. Thank you very much.